Hello everyone, welcome to the last part on interval scheduling. In the last two parts, first part we saw the problem definition, second part we talked about greedy algorithm for the unweighted case, and this part we'll talk about weighted case and a dynamic programming based algorithm. So we'll just go to the weighted case first, and this is the problem. So we are given n jobs which are 1 to n. Each job I is for some time period Si to Fi. Si is the starting time of job I, Fi is the finishing time of job I. And they have, each job has some weighted value Vi. And our goal is to select a subset of jobs which are mutually non-overlapping and a subset of intervals of jobs. Here I'm using intervals and jobs interchangeably, so as to minimize the sum of values of all these jobs which are there in S. And we saw earlier that interval graphs are related here, and independent set interval graphs are related to independent set interval scheduling problem. In fact, you can again check the weighted independent set in interval graph is equivalent to weighted interval scheduling. And the last part we talked about the special case when all values were equal, all VIs were 1, the cardinality case or the unweighted case. And in that case, we found that there is a greedy algorithm by earliest finishing time. But as we mentioned earlier, that mostly greedy will not work. Problems lack structure where greedy will work. Greedy is good to understand some basic structure about the problem to try out. But then once we know the structure, we should try dynamic programming. In this case, let's try out the greedy once more. We can use the previous greedy and we see here, for example, if I have jobs, these 3 jobs, optimal is 2, I'll select, sorry, optimal is 10, I select a single job. Whereas the algorithm will select 1 and 1 by the greedy strategy where we select the earliest finishing time. Greedy 2, maybe in this case we need to focus on the weights. We sort them according to weights and take the highest weight item or interval and continue. For example, that will work in this first example. I'll take 10 because it has highest weight. But it will not work always. For example, take this example. I have highest weight job 10, but that will be the solution by this greedy strategy. But 6 and 6 can be taken, which will give more value. One can try maybe other approaches, divide and conquer, or some other way of dividing, but that is not clear. So how do you use DP? Let's recall, in DP, I mentioned these elements of DP. We need to find some ordering, then prove this optimal substructure theorem, which will have recursion, and we want to show all the subproblems are there. It's all, but the numbers are still small. It's still polynomial time. We can find in polynomial time. And then we build a table, and then at the end, we discuss the runtime. Now for ordering, we need to find some ordering, and already we saw one good ordering, which we used earlier as well, is the finishing time or starting time, one of this ordering. So let's start with the finishing time, because we might want to argue from the end that if I select a job or not, what happens? So we sort the jobs according to their finishing time, non-decreasing finishing time, so F1 to Fn. This is the finishing time. Now, if we see an example, let's say some items are there, and if we have sorted them according to their finishing time, if I consider some edge, some particular interval, I cannot take any interval which overlaps with them. So if I sort them, the first interval which does not overlap with the interval, that is the one. After all the intervals which are following that will not take that. That is formalized by the notion of Pj here. So define Pj to be the largest index I less than j such that intervals I and j are disjoint. And if all I preceding j are overlapping, then we define Pj equal to 3. So it means that j and whatever is following Pj, let's say Pj plus 1, Pj plus 2 up to j, all of them overlaps. So I take this example. So here we have this job with some values. Now we have sorted them. The numbering is sorted according to finishing time. If I take job 1, let's job 5. Here, if I take this, I cannot take this job because it's overlapping. So, but V3, I mean, this third job is not overlapping. So in this case, P5 is 3. After 3, everything is overlapping, but 3 is the largest index such that 3, all the jobs before 5 are before 5 and after 3 are intersecting. So similarly, P4, we can see it's intersecting with all of the previous jobs, 3, 1, and 2. So it's 0. P3 is intersecting with 2 but not 1. So P3 equal to 1, and P2 and P1 intersecting with all the previous jobs. So it's 0. Now we need to find our recursion. And for that, let's look at optimal substructure. And as I mentioned, if we look at this ordering and look at the last job, there could be two situations. Either this last job is part of the optimal solution, if n is part of optimal solution or not. If it is not part of optimal solution, then fine, whatever is the optimal solution, that's also a subset of 1 to n minus 1. So you can just focus on the optimal solution to 1 to n minus 1. This kind of trivial if you think you will find out. Second property, if it is part of O, then for any I which is from Pn plus 1 to n minus 1, all of them will overlap with this job. So they cannot be part of optimal solution because already n is part of optimal solution. So O must include optimal solution from 1 to Pn. Now this looks kind of trivial, but let's still think why this is true, this optimal substructure property. For the second property, let's say we define OPn to be the optimal solution to jobs from 1 to Pn. Then if we take the union of OPn and n, that is also a feasible solution for the interval scheduling of 1 to n. And as O is optimal and this is a feasible solution, the value of optimal can only be more because it's a maximization problem. And similarly, we can say that O minus n is a feasible solution for the interval scheduling of 1 to Pn. Because if I add all the jobs which are there, none of them are overlapping jobs from 1 to Pn. Because none of the jobs from Pn plus 1 to n minus 1 are part of this O. So in this case, this is optimal and this is a feasible solution. We had this property, and this two combined gives us equality. One is greater than equal to, one is less than equal to. The combination gives us equality. So this is the optimal substructure property. And as we see, it is all and small. So so we can write the recursion first and then we'll explain. So recursion is this, that if I define opt_j equal to value of optimal solution for jobs from 1 to j, and then we define base to be opt0 equal to 0, then from the previous observation, we are getting that from this optimal substructure property, we get that opt of j is max of either opt of j minus 1, where j is not present, or if I take j, I get value j plus opt of pj. We recurse on the smaller subproblem. So we have only two subproblems to consider, and this is small, and this is already sufficient. All subproblems that are needed are there. Now for table building, we can do simple bottom-up iterative approach following this recursion. Base case is 0, and then from 1 to n, we simply build by the recursion. So it's a very simple algorithm. Already it works. Now if we go over again elements of DP, the ordering was based on finishing time. Then we talked about the recursion and independent overlapping subproblems. We have a lot of subproblems, but the resources for one subproblem is not creating problem for the other subproblem. We have kind of subproblems are not using the same resources. So if we take let's say we talk about opt, we have an item n, we take n, and then the remaining part, whatever we do, we can still add n. It is not creating problem with adding the n in a recursion formula. And then we are talking about number of subproblems, order n only, not too many subproblems from m0 to mn. So all problems are considered in the table, and the table building will again not take too much time because the number of table entry is only order n, and for each time we are only checking 2 entries, so it's constant time. So overall, it's a linear time algorithm. It's even better than the n log n or time algorithm what we discussed in the unweighted setting. So this ends the weighted interval scheduling. In the last part, I will talk about some advanced topics. You can skip it if you're in a hurry. So this is also one of my this problem of interval scheduling is also very interesting to me. So I have worked on several interesting problems related to this. For example, if I give you an online problem, if the intervals are not known a priori, they come one by one, then what can you do? So there's a recent paper in IISa on this topic. Or there is another very important question of intersection graph of rectangles. So maximum independent set of rectangles, where we are given some bunch of rectangles, they can overlap, and our goal is to find maximum number of disjoint rectangles. It's a very fundamental question in computational geometry. Many czars have worked on this problem, And recently we gave an improvement of 3 approximation in soda, and then there was a follow-up 2 plus epsilon approximation for the problem. And this problem uses something called guillotine cuts. If you have noticed, this is the channel picture, and this is the guillotine. So guillotine is referring to this technique called guillotine cuts, which we have used in the problem. So this is a problem which is very close to my heart, and there is a 2-hour talk I gave on this problem on recent trends in algorithm. I'll post a link if you're interested in research or know what are the cutting edge research problems in interval scheduling. Then I'll post them in the comments. And with this, also I would like to mention that this is another figure from this paper, which I really like. It's a magical bird, I call. So this interval scheduling problem, we started with this magic of Hermione, and we end with the magic of computational geometry. Hopefully you like this. Thank you.